we'll talk about minimum spanning tree. There are two algorithms associated with it, Prime's algorithm and Kruskal algorithm. We'll not be talking about the time complexity analysis nor the anything related to time complexity analysis. We'll be just looking at the algorithm with an example and where do we use it and how do we use it and how do you find a minimum spanning tree from using these two algorithms. Motivation for studying these algorithms is given in another video. Okay, so and the video name is motivation for studying minimum spanning trees. So now let us, without any delay, move into the algorithm itself. So the definition of a minimum spanning tree, that is, for example, you have Prim's or Kruskal's algorithm. Okay, you have Prim's or Kruskal's algorithm. To this, if you pass your graph as an input, the output of this algorithm, that is either you have Prim's or Kruskal's, and to this if you pass your graph, output of this algorithm will be a minimum spanning tree. Okay, that is, for example, if this is a graph which you have, undirected graph, undirected weighted graph, okay, and these are the weights associated with them. Okay, and let us see output of your that is a minimum spanning tree is acyclic. It does not have cycles. That implies that from A you can reach B, from B to C, and again C to A. This is a cycle. That is the point where you start, again you can reach to the same point. Okay, using the edges here. So when this happens, you call it as a cycle, and usually this is avoided. We don't want cycles. Okay, and here, and also now in your minimum spanning tree, and this sort of conditions will not be available in your minimum spanning tree. And here what we have done is, here for connecting all the nodes we have used total of 1, 2, 3, 5 edges. Okay, and usually 5 edges are not required for us for connecting all the vertices here. So these are called as vertices or nodes. Okay, so we don't require, these are called as edges, these lines we call it as edges. We don't require 5 edges to connect all the 4 vertices here. So what will be your minimum spanning tree if you pass this graph as an input argument to this Prime's or Kruskal's algorithm will be, you have 4 nodes. Obviously 4 nodes will be connected, but all the edges will not be required for us. So for A and B can be connected in this way with the edge cost of 5. Okay, B and C can be connected here in this way, and C and next what will happen is, and C and D can be connected in this way. So as you can see, it is a connected graph. This graph is connected. That is, all the nodes are connected to us. All the you can reach any node from any node, and you don't require, and we have eliminated some edges here. Okay, and this minimum spanning tree does not have a cycle. That is, given a graph, what you do is you convert it into, given a graph, you convert it into a minimum spanning tree. In this minimum spanning tree you don't have cycles. That is, A to B, B to C, C to A is a cycle, D to C, C to B, and B to D is a cycle. That is a point where you start, again you reach there. Okay, if that provision is available in the graph, that should be avoided. So here you don't have a cycle, it's a cyclic graph. And if this is a graph, this is a subgraph of it. This is a subgraph of this graph. Okay, and all nodes are connected. Okay, so these are the features of a minimum spanning tree. And why do we require it is explained in another video, motivation for MST. Okay, now let us look at the Prime's and Kruskal's algorithm. How do we use them to obtain this minimum spanning tree where all the nodes are connected and it is acyclic, and all the nodes are connected using minimum edges here. So let us look at Prime's algorithm here with an example. Consider this graph. Okay, this is a undirected weighted graph, and this is an array. So this is an 8 by 3 array. So instead of while implementation, this will be your matrix. Okay, this will be your matrix. So you will be declaring it as int array of 8 by 3. Okay, array, and this will be your 0 1 2, and this will be, so that is about implementation. We'll talk about implementation in later classes, but take a look at this table. Let me explain these tables to you here. So these are your vertices or nodes. Okay, F implies that none of the nodes have been visited till now, that is we are not visited any one of the nodes. It implies F means false. If you have visited any one of the nodes, it becomes true, T. Okay, and cost of reaching every node is infinity, that is we are not visited, we are not started the process, so initially everything is infinity. We don't know what cost is associated with reaching every node, so we make them everything as infinity, and none of the nodes are visited. So this is the initial condition. Now let us start from any, we can start from any node. Okay, so to find my minimum spanning tree for this graph, we can start from any node, but for example we'll start from the node D. Okay, so here if you look at, I have started from node D. Whenever the circle becomes red, that implies that I have visited the node. I make it as true. Okay, and cost of visiting this node is 0, because this is the first node. I have not come here from any other node. This is the point where I start. Okay, so there is no cost associated in reaching this node. So this is the initial node from where I start, and P implies here parent node. What is the previous parent node from where I have reached here? So there is no parent node to D, because this is a starting point, so it is as hyphen for us, null. Okay, so this is the first node from where I start, so there is no cost associated with the no cost associated in reaching here, and does not have a parent node. This is a root node, or initial node from where I start my process of finding minimum spanning tree. Now staying here at this, from this point, what are the nodes or vertices which I can visit? I can visit C with the cost of 3. I can visit F with the cost of 18. I can visit G with the cost of 2. I can visit E with the cost of 25. These are the 4 possible nodes which I can visit. Okay, so whenever you visit a node, first write down the possible nodes we can visit from that particular node, and cost associated with reaching the node. That is, what is the cost associated with reaching C or F or G or E. Okay, that is what we have written here. Okay, so from D, cost associated of reaching C is 3, and if you take this path and if you reach C via D, parent node for C will be D for you. Okay, and cost associated with reaching E is 25. Okay, and if you reach E via this path, the parent node for E will be D for you. Similarly, cost associated with reaching F is 18, and if you take this path, the parent node of F will be D. Cost associated with reaching G is 2, and if you take this path, parent node of G will be D for you. Okay, so this is what we have written. Now out of all these possible paths which I can take, I will be choosing the minimum path which is not visited. For example, out of these 4 paths, what is the minimum cost path for me? G, right? And G is not visited. Okay, so what are the conditions? So out of all the possible paths which I can take, I have to find the minimum one which is not visited. Okay, that is, here you have blank or F which is not visited. So I take the path G. So what do I do is I move from D to G. Okay, so I'll be having a red line here, which implies that I have started from D, then I have taken a minimum path, and I have moved to a node called G here. Okay, so once I am at this point, that implies that I have visited G. So these were the possible nodes which I can visit from D, but I have taken the minimum one, which was 2, and I visited G. That implies that G is visited for me. I mark it as 2. Now the same process, staying at G, I have to see what are the possible nodes which I can visit from the node G. Okay, one possible node is H. Okay, H is not visited, so I'll be writing here the cost associated with reaching H is 3, and I'll be having the 3, and I'll be having the parent node for H will be G if I take this node. Okay, I have not visited it, but if I take this path, parent node will be G for me, and the cost associated will be 3. Next, and the other thing is, I can also reach E. Okay, and the cost associated now is 7. Okay, but here what has happened, previously when I was at D, from D also I can reach the edge of the vertex or the node E using the cost 25, and if I take the path D, I'll be requiring 25 units, that is the weight associated is 25, and if I take the path of G, weight associated is 7, and E is not visited. So what do I do is, I'll be comparing, that is cost of reaching E via G is 7, cost of reaching E via D is 25, which one is minimum for me? So this path is minimum for me. So what will happen is, this will be overwritten as 7. Okay, and what is the parent node now? Instead of D, I'll be having G here. Okay, that is previously cost of reaching E via D was 25, but here what is the cost of reaching via G? It is 7. So this path is less expensive when compared to this part. So what do I do is I overwrite it. That is what we have done. Okay, now what are the unvisited nodes for us? So 1, 2, 3 and 4. These are the unvisited nodes for us. Again the same process we have to do, that is we have to select the minimum cost edge, the minimum cost path of unvisited nodes. So here these are the unvisited nodes, and the minimum cost here we have 3, 7, 18 and 3. So here we have an ambiguity, that is we have two edges with the same cost, which one to choose. For our algorithm, whenever we have a dilemma, so we'll follow the alphabetical order. The alphabet which comes first will be the node which I'll be, with the edge which I'll be selecting. Okay, so what do I do is, here I select the node called C. Okay, so how do I reach C? Via D. Understood? So out of all these three, the minimum cost is C for me. And how do I reach C? Because I have to reach C, right? I just can't arbitrarily start from C. So from how do I reach C? With the parents, what is the parent of C for me? It is D. That is what we have done. Okay, so now what happens is, I have visited the node C here. Okay, and I have made it as true, that implies I have visited here. The same process now, what are the possible nodes which I can visit from C? Now here I can either visit B, F and D. I cannot visit D because D is already visited, so I have to only check for the unvisited nodes. So B and F, so these are the two nodes which can be visited. So C to B cost is 4, but if you look at here, okay, there is no cost here. So what happens is, cost of reaching B will be 4 for me. Okay, and what is the parent node here which I have? C. Next, I also have a node called as F. Okay, so F can also be reached, but previously F was reached by a D in the cost associated was 18. Now what is the cost associated of reaching F? It is 3 via C. So what do I do is, 3 is less than 18, so obviously this will be overwritten. So cost of reaching F will be 3, and now instead of reaching F via D, I'll be reaching it via C. Okay, that is what we do here. That is the modification which we have done. Now out of all the unvisited nodes, that is 1, 2, 3 and 4, we have to select the minimum cost edge here. So the minimum cost edge where we have is 3 and 3, that is F and H. So now what do we do is, we go by alphabetical order. So we select F, and how do I reach F? Via C. Okay, so I mark this as true because I have visited the F now. Now staying at F, the same process has to be repeated. What are the possible ways of visiting unvisited nodes? Red circles are visited nodes for us. So F2A takes me 10, so there is no path from F2A previously, directly I can write it. So F2A takes me 10, and the parent node for it is F. F2B takes 7. What was previous cost here? It was 4, and 4 is less than 7 for us, so we don't do any modification. That is 7 is greater than 4. Cost of reaching B via F is 7, but previously cost of reaching B via C was 4 for us. Okay, so we don't do any modification here. then F to D, D is already visited for us. Okay, F to C and C is also visited for us. Next we have F to E. Okay, now here if you look at E, what was cost of reaching E here previously? It was 7 and it was via G for us. Okay, so what do I do is, now what is cost of reaching F to E for us? It is 2. So 2 is less than 7. So what happens is, this gets updated to 2 and the parent node here will be F for us. Okay, so these are the modifications which happens. Now again the same process, that is select the minimum edge 10, 4, they have 10, 4, 2 and 3. So minimum edge is E for us, so we start with E. And how do I reach E? Via F. So there will be a red mark here. Okay, so this is how I reach it. Now staying here, from E what are the possible nodes which I can visit? From E, D is already visited for me, G is already visited, and only node which is not visited is B here. And what is the cost associated with reaching B? Previously it was 4 and it is via C, but now what is the cost associated here which I have is 10. 10 is greater than 4, so I don't do any modifications at all. Okay, so E is visited for us. Table entries are unchanged. Next, now what is the next minimum unvisited node here, which you have 10, 4 and 3. So 3 is the H is the node which you visit, which has less to visit. And how do I visit H? Via G. Okay, so staying at H, what are the possible values, possible nodes which I can visit? H to B and H to A and H to G. H to G is already visited, so I don't consider this. H to B is 9. Previously what was the cost of reaching B? It was 4 via C, so 4 is less than 9. I don't do any modification. If and only if this value is less than the value which is available here, I do modification, I change the parent node. Okay, so and next H to A is 4 for us. Previously cost of reaching A was 10, which was via F, and now reaching A is A cost is 4 for us. 4 is less than 10, so 4 gets updated and parent node will be H for us. So this is the only modification which happens. Okay, now we have two unvisited nodes A and B. Out of this, both the costs are same for us, so we choose alphabetical order. A gets selected, so A is marked as true, I visit A, and only unvisited node is B, and cost of reaching B is 8. Previously cost of reaching B via C was 4 for us. Okay, so 8 is not less than 4, so there is no modification for us, and there is no modification. Then out of only node which is unvisited is B for us, so B gets selected. Okay, table entries are unchanged. Next B gets selected and it is also marked as true. If all the values in this column are true, that implies that you have visited the entire nodes and have got a minimum spanning tree, and total cost associated here is 21. So this is your minimum spanning tree. So as you can look here, previously you had all the nodes are connected and there were multiple paths for reaching each and every node. Okay, so instead of having multiple paths and instead of having cycles, that is, if you assume this as a network and this as a city, every city has multiple paths associated with it, and these are your optical fibers which are laid to connect all the cities. Okay, and laying optical fibers, maintaining optical fibers, okay, is costly affair for us. And if you are a person, if you have a BSNL server here at each and every, okay, if you have a server, not BSNL, if you have any server at each and every city here, and if you want to connect them, so, and obviously this optical fiber will be laid by the government or any ISP provider, and he will be charging you. If you use this path, he will be charging you. Okay, so what I have to do is I have to connect all the servers in the cities with minimum cost. How do I do that? I will be finding a minimum spanning tree. Okay, so that is what is one applications of having the minimum spanning tree. So this is about the algorithm. Next we'll talk about Kruskal's algorithm. So this was your previous algorithm. So we'll talk about Kruskal's algorithm. In Kruskal's algorithm is simpler. Here what do we do is, given a graph, okay, given a graph, we sort the entire edges. Okay, so given a graph, we sort the entire edges. That is, here we have D2 is 1, this is the edge with the shortest, with the lowest edge cost. D2G is next lowest and E to G is next lowest. So we sort all the edges here. Okay, and next what do we do is, first edge is D to E, so I mark it. Okay, this is visited, this edge is completed for us. That is, I mark a connection between D to E if it does not form a cycle. Okay, if it forms a cycle, I just I don't mark it. Okay, okay, so then what and also if this marking this edge leads to a cycle also, I don't mark it. Okay, so these are the things. That is, for example, if D and E are unvisited and having this edge, making this edge forms a cycle, then I don't do anything. That is, D and E are visited and making this edge forms a cycle, I don't write this edge. Apart from that, I write it. Okay, so D and E, if I connect D and E, it doesn't form a cycle because all the nodes are initially not connected for our assumption purpose. Okay, so I have a connection between D and E. It's a lowest cost, it doesn't form a cycle, and both of them are unvisited for us. Okay, no problem here. Next what do we have? Next we have D to G. So D to G can also be marked because making this doesn't form any cycle. Okay, next I have E to G. If I make this, what will happen is it forms a cycle, so I don't make it. Okay, so that is what we'll be doing here. So D to E gets formed, D to G gets formed. Accepting could create a cycle for us. Okay, that is why G to E doesn't get formed. Next you have C to D. So C to D will be formed for us. Okay, next you have G to H. So you have G to H will be formed because it doesn't form a cycle here. Next you have C to F. C to F will also be formed, there is no problem. Next you have B to C. B to C will also be formed here, no problem for us. Okay, next you have B to E. If you have a B to here, it forms a cycle. That is, if you have a edge in this way, what will happen is B to D, D to C, C to B, B to E. So this forms a cycle, so this is avoided. Then you have B to F. B to F is also a cycle for us. If you have edge in this way, you have a cycle here. Okay, B to H is also not allowed because if you have a edge here, what happens is this forms a cycle. H to A can be allowed because it doesn't form a cycle, and D to F will not be allowed because you need to have, when you have edge here, it forms a cycle, so it is not allowed for us. So other things are not considered because already all the nodes are visited here. Okay, D to F. Next you have A to B. Okay, A and B are visited for us, A and F are visited for us, so we don't consider here. So what is the total cost which we have associated here is 21. So this is the minimum spanning tree when we use Kruskal's algorithm. Okay, so what is the process? Only thing which you have to remember is given a graph, you have to just sort all the edges. Okay, you sort all the edges and then you connect each one by one, and if you connect only if and only if they doesn't form a cycle. Okay, otherwise you can connect them. So that is about Prim's and Kruskal's algorithm for finding minimum spanning tree. So here, so how do you represent a graph in programming? Suppose if you have a graph, okay, so these are the edges associated with it. So how many vertices do I have? 1 2 3 4. So I'll be having a 4 by 4 matrix. Okay, so assume this as A as 0 vertex, 0 node, 0 vertex. So first vertex, second vertex and third vertex. Okay, now similarly here also you will be having 0 1 2 and 3. This is your matrix which you have. Okay, now I have an edge between A and B and the cost associated here is 1 for me. So from 0 to 1 we assume that instead of A we have 0 and B we have 1. So 0 to 1 I have an edge and the cost associated is 1 here. Okay, next from A to, let us see here. So from A to D I have a edge and cost associated here is 5 here. Okay, that is 0 to 3 I have a edge, so obviously and the cost associated is 4. Then from 0 to 2, that is A to C, I have an edge and the cost associated is 2 here. 0 to 0 I don't have an edge, so obviously it will be 0. So 0 implies, and 0 implies no edge, and any other value apart from 0 implies there is an edge, and the value is nothing but the cost associated with that edge. Next you have is 1 to C. Okay, so 1 to C means 1 to 2 and the cost associated is 4. Next you have is 1 to 0, that is B to A, and cost associated here is 1. Then you don't have an edge between B to D. Okay, so and other values are zeros for us. In this way you represent a graph. Okay, and once you have this, you can implement the entire algorithm for it. Okay, so implementation things we'll be talking about in the next video, and also motivation will be talked in the next video for us. Okay.